Okay, first the intro. Sorry, first the intro. I have to make an intro. So, hello and welcome to the first Feder und Schwert podcast with today's guest. I'm very excited that he found a time and he's joining us. He's a very well-honored professor and geologist at the University of Roma TRE, as well as from the endowed chair of structural geology at the University of Texas at Austin. Bestowed with, just to name a few, the Galileo Galilei International Medal for Earth Science, the Humboldt Research Award, speaker at the renowned Francis Birch Lecture, and at least 3 more pages of honors, memberships, editorials, professorships, services, projects, not counting the publications. And I'm very happy to have him here today, Professor Dr. Claudio Faccenna. Thank you very much for joining.
Thank you, Matthias.
And Professor, for the introduction, and this video is about storytelling. And my first question to you is, could one describe geology as the slowest, but in the end, the ultimate storyteller?
Well, geology gave us the possibility to read the story of the Earth. So in the history of the Earth, the human represent only a few seconds. And if you imagine 1 day of evolution, we are just very few seconds, very at the end. So geology gave us really the possibility to have a different perspective on nature, on the evolution of natural system through time. And so for us, speaking about million years is something that is not really represent anything weird or bizarre, but we are fully into a completely different time scale with respect to the human one. And this gave us a very great perspective on the small impact of the human, a big impact we are doing actually, but a small in a way on the history of the Earth.
Is it scientifically fair if some people are speaking about the geological time of human impact, that it could even be framed as a geological time space, not even anthropocene?
That's a good question, because the impact we are having on the evolution of the system, of the Earth system, is pretty big in terms of altering ecosystem and also the atmosphere and the climate. As we all know, our impact is very strong. Therefore, we call it Anthropocene now. Is a new era that is evolving, and we always thought, it will be marked by a lot of plastic, for example.
Yeah.
And this will be terrible actually when the layer the layer of soils and rocks will form. Then we will have a layer of our production that sometimes will be permanent, and the impact is permanent. So it's a very strong impact, I'm afraid, even though the time scale is very short. It's going so fast that it's really impressive and scary.
What do you think? Like, if we go into the future, like 1 billion years, like a really big time scale, a geological big chunk of time into the future, what would be the most striking evidence that we are producing right now? Would it be the plastic, or would it be like radioactive stuff? Would it be like the nuking sites, or would it be how would you start looking for evidence that we were there?
If some other being will look at the rocks and the record in the past and say, well,
yeah,
those are the humans' impact. Well, that's an interesting question. I never thought about that, but yeah, for sure. We will have this very high peak of CO2 concentration, and also of that is recorded with the temperature rising. And this is well known. It's well recorded in ice and in rocks, in the carbonate, for example, that are depositing now on the ocean. So And maybe who knows what will be the consequence of all that. I mean, in a short time, but we may have a big impact on ecosystem. The history of the Earth has been punctuated by very rapid and sharp change in completely the biosphere, and the biosystem collapsed down several times during the last 600 million years, for example. It's not only the dinosaur disappearance, but also before, and the Permo-Triassic, we had almost 90% of the species that were disappearing very sharply. And this has been due probably to a big impact like a strong eruption or big volcanic emission that alter completely the atmosphere and the climate, and also the concentration of several chemical elements in the water that are creating unfavorable condition for life. And what we're doing is basically going in that direction in a way. So we maybe not only plastic and radioactivity the score that we are accumulating, but also maybe, and a lot of hydrocarbon, of course, but maybe also some big, massive extinction and impact on the biota will be registered in the rocks. So I don't know. I mean, we will not be there.
Yeah, they will have to find out. Yeah.
Exactly.
So, if we're talking about changes and those big time scales in between, what are the big players? Like, we know that we have that tectonic shift that is colliding. Plates are colliding and are drifting apart, and then we have something like a withering. Like you have weather, you have atmosphere, you have river systems. Are they playing at completely different time scales, or are they close to each other that they are smearing over one and each other?
Oh, this is a very good question, actually, and there are things that there's an entire community working on. We realized during the last 10 years or so that the different shell of the Earth cannot be treated separately. So we realizing more and more that the effect of deep mantle convection, for example, the convection that is occurring in the Earth interior between for 1,700 kilometers and the 100 kilometers, so producing this large slow movement of rocks interacting somehow with also with the surface and producing surface deformation like uplift and subsidence, and also movement, as you say, of rocks laterally drifting apart, so bringing continents one against the other and rising mountain belt. But also, these have an impact on the atmospheric circulation and on the migration and dispersal of not all mammifers, for example, of other species. You may think, for example, the rising of the Himalaya created the monsoon. The monsoon has an enormous impact on the atmospheric circulation, and it's probably the rise of the Himalayan Tibetan plateau is probably occurred in the last 30, 20 million years, something like that. And this is considered to create a depression, for example, in the North Africa and in the Mediterranean. So part of the desertification and the climate that we have here in the Mediterranean is probably also due to the fact that we have the forcing of the monsoon against the creation of the monsoon, because you have a mechanical barrier for the flow of the moisture coming from the Pacific that go against the barrier and so discharge the large rain. So everything is coupled. The tectonics is coupled with the climate, and also a lot of getaway creating. For example, one of the best known one is the one that provide the possibility for mammifer dispersal from Africa to Eurasia, and this was creating during the approaching of Arabia against Asia. And so this getaway, this land bridge, create the closure of the Indian Ocean, and this connection between the Indian Ocean and the Atlantic Ocean, because create a land bridge. And in this land bridge, around 56 million years ago, a lot of elephants going, and a lot of mammifers are moving into Eurasia and dispersed there, but also humans start moving northward because of looking for other conditions. For example, if the desertification of the North Africa was keep going, then it's forcing some humanoid, not the one that then after created the Erectus, but it was something preliminary around the middle Miocene, start moving northward and then extinct. And then afterwards, in the late Miocene, we have another pulses of humanoids migration. This is so interesting because the creation of getaway, probably also the disconnection between the two sea, created a large mass of salt moving to the Atlantic and producing probably a big change also on the circulation. So you see from this kind of example, the other striking example is the closure of the Drake Passage that created the Antarctic glacier. So, or the closure of the Panama. It also created the northern, created change in the circulation and created the ice, the ice in the northern pole. So the impact is so big, and this is coming from tectonics. So the tectonics interact with the surface and with the climate and biodiversity. So you go from deep to the mantle on top of the atmosphere, and everything is interconnected. We are discovering crazy and very unexpected linkage between discipline and fields that previously we didn't expect, actually. So also the river incision and the way the glacier work on the mountain may interact with the tectonics, may interact with the climate, and interact with the motion of the plates. So, and this feedback create a completely new field. We are realizing in the geoscience, in earth science, but in many other fields the same, that the big discovery coming really when you go in this gray field between discipline, and if you are able to fill the gap that are left behind the discipline, then you may really realize and discover big new unexpected interaction or feedback like the one we were discussing.
Yeah, you've worked very intensively, I take it, on a model of representing the tectonic plates and the mechanisms that are driving it. Did you always have to assume that the tectonics are interconnected, but nothing is really pushing tectonic itself because it's such a big motor in of itself? But I've heard this theory that during Ice Age there was an ice shield on the North American plate, and when it was melting there was so much weight gone from one plate that it was like going up a little bit and making another one because they're in balance going down. So that would mean that actually there are things that are looping back into the tectonic movement itself. Is that possible, Bob?
So I mean, the impact of during the last 5 million years, but especially during the Pleistocene, we have this glacier interglacial stadium, the stage that we know very well related to the orbital motion of the Earth, and so the distance with the Sun. This created, of course, a period of big glacier, as you say, the distribution that, so the last glaciation was creating glacier arriving down to Northern Europe and also North America, New York and things. So when this glacier start melting, they create, of course, the compression on the mantle behind. And so the adjustment created by that was a motion, as you said, of the land that go up. The velocity of it's very interesting because this was studied first by a Norwegian scientist, Askell, in 1936. He realized, actually, studying the little the age of the notches left by the uprising had with the land with respect to the sea level, and the age of that. He reconstructed the velocity of the uplift, and he realized that the velocity is not an elastic movement, but is a viscous process that is bringing up the mantle, pushing back the land on the previous position, and so the mantle was following that. So the velocity is driven by the mantle viscosity, and we learn from that curve that he reconstruct about the viscosity of the Earth interior. So the Earth interior is done by solid rocks mostly, but in terms of geological timescale, it behaves like a viscous, very, very, very highly viscous fluid. The melting, as you say, because of that behavior, the water that it created, melt and cold water, was of course going into the ocean, and then was loading the ocean. So while you are unloading the continent and loading the ocean, and this created a readjustment of the entire globe. We call the glacial static adjustment, and so all the sea level was readjusting around the globe, and it takes sometimes. It is still going because we have the northern Scandinavia land, for example, Greenlandia or the northern Canadian, it's uplifting, it's keep uplifting because it's a viscous, long-term process during the melting. And other land, and then the ocean are subsiding for that reason because you are melting and water is going. So you're readjusting completely the surface of the Earth.
If you're
yeah, go.
The lag was a little bit there. Sorry. If you're then speaking about mountains and viscosity, that means you're thinking of almost like fluids and fluid dynamics that are interacting on the complexity scale.
Yes. Actually, I mean, there are processes that you can approximate the behavior of the geological behavior of the Earth in a long-term process may be approximated on a first approach as a viscous fluid, non-Newtonian viscous fluid. So it's a Maxwell fluid with a Maxwell. It's a viscous. Of course, when you go on the surface of the Earth, the rupture that you are creating during this motion and the big fault that you are creating, those obey to another kind of law and are more elastoplastic. So you are creating fracture and you are loading material and unloading elastically to release earthquake. So it's really all depend on the time scale of observation. On the long term, we can, a million years, you can approximate that the motion of the plates and the motion of the mantle is going at the velocity of a centimeter per year. That's the rate. So, but you can have a process going a meter per second when you have an earthquake on the surface. And this is all connected, but the geological response is different.
Now, I remember seeing a lot of animations online and in school where they have mostly a drifting apart. It always looked like there was and they say there's the supercontinent, right, and then it drifts apart. That was the image that I took from my geological education at school and what I saw in documentaries and so far. If you take the supercontinent drifting apart and you compare it to the complete age of the Earth, is that a cycle in and out of itself, always this drifting apart and then being condensed together to a supercontinent again? And then is there some sort of a breathing going on?
A very nice images, the breathing idea. Yes.
Thank you.
I mean, this is of course coming from Wegener, no? The first images of his theory of a Pangea and continental assembly that was happening in the late Paleozoic. So the sign was clear. I mean, there were signs of the same rocks on both sides of the Atlantic, the same fossil, the same volcanic unit. So everything was very perfectly correlated. So once we had the possibility to look what happened, for example, in South Africa or in the Brazil, then we realized the rock are the same, and then we can put it together things. And at the time, at the beginning of the last century, we already have this kind of information. So of course, Wegener make the reconstruction that was really well in time, well done for the time, and actually is still very active. Its theory was not really accepted immediately, just because it didn't have really a mechanism to explain that. This came later on when we start discover the nature of the ocean that was not known at the time. So what we have behind the ocean is different from the continent. So it's a new seafloor and spreading story that is the origin of the plate tectonic theory that we have now. So it is true. When you go back in time, the small continent was approaching each other in cycle, kind of supercontinental cycle. There was not only one. The one we have now is the oldest one is Pangea, and then we probably have another one in the future. And when, for example, if the Atlantic will closing again, then we will have again the approach of America and Eurasia, or if the Pacific will close, then we will have what we call Amasia. So the America will join Asia, and then the Pacific will go down into the mantle, and then we have another ocean opening on the other side. So this is a two kind of possible scenario that we imagine, either closing the Atlantic or closing the Pacific, which will take different time, and it's a different kind of process. When you go back in time, you have other assembly. One happened 1 giga years ago, which is Rodinia, and then another one around 2 giga years, which is called Luna Columbia, and another supercontinent. And then again, even farther back, 3, we have supercratons called Sclavia or other supercratons that I don't remember the name. So it looks like we have cycle of that process, and there was a lot of work trying to understand if those cycles derive from the breathing of the earth, as you say, from, for example, thermal insulation. So when you create a supercraton, then you create a condition below of heating up the mantle below, that then create an upwelling and then dispersal. Or if there are conditions on the side, for example, the subduction zone, when the ocean descends into the mantle, they may really go very down or just staying a little bit shallower. So the way this may happen may have influenced then the possibility of the continent to disperse up again, to drift apart. So there are competing theory and different ideas on that. This is really interesting topics, and there are a community working on supercontinental cycle. It's really interesting. This also may have an effect also on climate, for example, change, and on because when you have continental assembly, you create mountain. If you create mountain, you have erosion. If you have erosion, then you can have the CO2 sequestration, so the temperature may go down or up as a function of the amount of material you are eroding from a mountain. And so there may be a link also with the temperature and the climate, and so a link on the possibility to have life on Earth and the ability of the Earth when it starts. This is a wonderful, interesting question. It's more and more important to understand what was really the condition to have the Earth ability also to look around other planets which may have the similar condition for the birth of life.
If you think of all those, let's call it cycles, that work through different time scales. Like, for example, you mentioned before that you have the monsoon, which is now in and of itself a cycle. And what I want to come to talk about is the desertification of the Sahara and how that affected the region, as you said before. Like you had this immigration, you had biodiversity, all this interconnection. So I take it now that there was the tectonic shift, and that made the Himalayas raise, and then that created some sort of a potential for the weather to change, or an interaction, because there was surface now coming into the atmosphere. And how would that interconnect with the wind system, or how would that then change the wind system of the or is the monsoon a wind system, or is it just a rainy season?
No, it's a wind system. It's a global circulation. The monsoon will change also the position of El Nino, for example, and have an impact on everything. And so it's the wind system. The topographic barrier created by mountain may largely affect the climate interaction, of course, and the climate circulation. For example, it has been seen by simulation that the uplift of the Iranian plateau, for example, the Zagros mountain, all there, and also of the Atlas mountain, may have created conditions for desertification into the Mediterranean region, something like 15 million years ago. But also the gateway, also the closure of the gateway from India and Mediterranean also created the same condition. So all these tectonic feature perturb the wind system. And so maybe the summer or the winter wind system bringing moisture from one side to the other. I'm not an expert on atmosphere, of course. I'm a solid earth scientist, but collaboration with atmosphere between the different disciplines is revealing more and more important to disentangle the effect of the cause and the effect on the signal that we have. For example, we had some climate optimum in the middle Miocene that we hardly explain really, and also we had in the Oligocene, for example, some 30 million years ago. On the Eocene, we have a climate optimum, sea level rise, and everything with CO2 level very high. So all those signals, where they come from, it's still partly unclear, but definitely they should be related to some also tectonic imprinting behind. So the way tectonic influence climate, and then consequently also all the biosphere, of course, and that has an impact. So, for example, the desertification of the Sahara is a very interesting point, and it looks to be started probably now. People found, for example, old sand dunes in Chad. It looks like before everybody was thinking that it was connected with the formation of the polar cap, the northern polar cap, like 2-3 million years ago. So the closure of Panama is influencing all that. Now, the founding of older dune system in the Chad around 7 or 8 million years. So people are thinking that maybe the Sahara is an older story. And so it may be also related to the closure of the gateway, the Tethyan gateway from India to Mediterranean, or the rising of the Himalaya and Tibet, that create that or other possible causes. But this is definitely something that has a strong impact also on human, because the uplift of Ethiopia also has a very strong impact. You probably change all the vegetation there, and so that became more arid. And so this was forcing the human the Homo erectus to move away from Africa and to go north. So that's a story that has been proposed so far. I mean, one of the reasons why we have the motion toward the north of the dispersal of the north of our species is derived basically from climate forcing and vegetation change. So yes, there is a strong connection. We don't really get everything, but there's a lot of work that is now moving in that direction more and more. And this all was already, interestingly, I mean, I was working a little bit on Humboldt just to make a completely different path. Alexander von Humboldt already saw a lot of interaction between the tectonics, the climate, volcanism, for example, human impact on the biosphere, on vegetation, all this. He was one of the first ones really to highlight that kind of interaction. Incredible.
I never knew, is the stream, is it named after him, or was he the one naming it?
No, after him.
Yeah.
Nothing to do. I mean, yeah, there are plenty of things that I was named after him in South America, especially where he's very, very famous, actually. So there are, I think, also butterfly, there are rivers, there are mountains, also in North America, and but this was coming after him, actually.
Now, of course, Mr. Humboldt, he was very famous for getting into the field and for taking hands-on research. And I imagine for a scientist, that is the best part, that when you can get out and experience what you are describing and what you're studying by standing there. Have there been places on Earth that you visited that made a certain connection, or that you just saw some, or had this immense scale of geological workings that was in the place?
This is a great question. It's a very nice question. I consider field work as an infinite source of inspiration, but not only for the things that you are observing during the day, but also what you are thinking during the night, you know, and it's a part of or maybe coming back with the flight, you know, or so it's a full story there. And every time you go in the field, you're collecting data, and this is a very also tiring work, sometimes very repetitive, and so you're collecting data and taking notes and taking pictures, sample, and drilling rocks or so. But at the end, it is also stimulated a lot when you come back and you are thinking, put things together in a very nice way. My experience is not if, I mean, I've been working in some places of the world, not everywhere, and be working a little bit on a lot of my time in the Mediterranean, which is a very interesting site to work on, because it's still mysterious in several aspects, and it's probably one of the best sites to study the way the mantle and the surface interact together. Because the approach of Africa to Eurasia is very slow, so you can really work on what is happening inside. But also other places are fundamental. I mean, for example, working in Colombia, where von Humboldt was being, and it was very inspiring for me, and also on the other side in the Cordillera of the Andes. But I miss a lot. I'm working in Africa a little bit. I mean, in Ethiopia, working in Antarctica was very inspiring. I had the possibility to do a field work there, and this was really interesting too. So every place has its own flavor and leave its trace on our knowledge. So when you then sit down, things are popping up together and merge.
How difficult is it to get to Antarctica and have research there and prepare? And
well, Antarctica is of course is difficult, but we now have a lot of expedition running, and every country, a lot of country has their own base there that's very well organized. So you can work really on trying to do a different kind of one of the best things you can do is really to reconstruct with the ice on the sampling the ice and having a reconstruction, for example, of the climate. This is, of course, a fundamental stream of research. We've been working on in Victoria Land, there's active volcanoes and very recent also tectonics. So if you think to Antarctica like an old region where nothing happens, not true. And there is an uplift, there is big volcanoes, big shield volcanoes that are very recent. Some of them are still active. And so was plenty of interesting features to observe. Coming there, I mean, it looks like in some places it looks like my background here. So not too far from what we have on a alpine kind of mountain belt. So except the fact that maybe there was more ice, but the fault was there, and also a lot of tectonics running with a record going down to the Paleozoic. So very interesting story. You can reconstruct there. The difficulty, of course, is that when you are in a remote camp, you have to sleep with there are tents, big tents. There are also some more solid construction to store material. But and then you have helicopters, so you move with helicopters. But you may have trouble if the wind comes and the weather change. Then you can stay for days without working, waiting for the better weather, and this may be a little exhausting. But it's a wonderful place to visit.
So, what exactly was the point of your expedition there? What information did you wanted to get?
Yeah, we have been working on this Admiratlity Mountain, north on the eastern, in Western Antarctica, in the Eastern Antarctica and the Ross area. So, and the Admiratlity Mountain, a very high mountain, and there was two fundamental points that we were looking at in terms of rocks. One was exactly when the uplift occurs, so when this mountain rise up, some of them was going up to 4,000 meters or more, and what was the tectonics that was creating the condition to have this deformation there, and also nearby along the coast there was a big volcanic field. So what was the condition to create these volcanoes? And so it was a more tectonic structural geology. On the side, we also be working on the more older history. So there was Paleozoic rock. We were interested to know more about this Ross orogeny, a very old orogeny that happened in the Paleozoic. So what was the condition to have that? So it was both very recent, which was more my interest, the formation, and what was occurring, and the oldest one. And what we learned is basically that is probably there was a mantle upwelling creating the big bulge that we observe in that area in the Admiratlity Mountains, so creating topography, tectonics, and volcanism. And this was active probably during the last million years or so, was giving really a trace on the landscape, and this was a very interesting science. At the end, we end up with a very interesting result, unexpected.
Was your approach on that one that you looked at the topology and at the geometry of all the surrounding, and then interpolated or made a model about how this geometry could have happened and then deducted from that? Or was it more like sample taking and then analyzing sampling of
Let's go together. We always do two kind of approach when we study a region. The first approach is going in the field, taking the sample, trying to date, having constraint on ages of on the evolution, for example, of a landscape, on the formation of a mountain, the formation of a fault. So trying to date, to give numbers more quantitative as possible. And on the other side, we try to do models. So we if you want to go deeper, for example, then you need also some data that can illuminate deeper on the Earth, for example, from seismology. So if you collaborate with seismologists, then you can have data that explore what happened in the crust or in the mantle and give you more ideas of what can be. And the model can be done also to investigate more the physical process that you have in mind. So to test if the idea that you realize looking at the rocks and looking at in collaboration with others at the deeper part, if the idea that you have in mind can be feasible in terms of physics. So you go behind the computer and you run models, or we also have tanks where we do fluid dynamic experiment, and we look at what happens if you change one parameter or the other, and testing. So if the physics, if the reconstruction that you have done is physically can be demonstrated physically, and if it has, and this go together. So you have an idea, you test in the model tell you that this idea maybe is wrong, you go back in the field, you collect other data, and then you go back to your model. And so this is creating a sort of iterative feedback action between what can be the data that you have to collect in the field and the model that is driving your ideas. So this is the kind of approach that we have, and I think it's the one that brings you very interesting. Of course, the model are limited and is not reproducing the nature. For that reason, the model, you're not reproducing the nature, you're reproducing the physical mechanism that you have in mind, which is make a big difference. Testing the physical, the idea that you have in mind, not reproducing. And because reproducing the nature is impossible, you can also do a model of the whole globe. We have a model. We recently done work with a numerical model, not run by me, by my colleague in France, for example, was running a model for 9 months of the entire Earth that was convecting and for the last exploring the last giga years, for example, and you can see continent moving around and things. It's a very long. I mean, to have one result, you have to wait 9 months on supercomputer running. And
that is a long time,
It's very interesting. The results are really interesting. You're not pretending to simulate the Earth, but the physics is probably we can learn something interesting from there.
Now, connecting this to back to Africa, and this time not to a mountain, but to the river system. And going to the Nile in the specific, you speak there about a deep mantle route of the River Nile. And now I take it for there was always this huge speculation, where is the source of the River Nile? There is this ancient long questions, and I think even a joke for the old Romans, where is the source of the Nile, or something like something you will never truly find. Is a deep mantle route, has it anything to do with some idea of a source, or is it something completely different?
It has some concept behind, and there is not only a discussion on the where the source of the Nile is. Now we know that, of course. I mean, the Blue Nile and the Tegese start from the Ethiopian island, from the Lake Tana, whereas the White Nile, rejoined the Blue Nile very recently, around 2 million years ago on the Pleistocene. Did come from further to the south to the Lake Victoria and River Nile mountain. So there are two different sources. one tributaries, which is the White Nile, that joined the Blue Nile very recently. We were more interested on the Blue Nile story, which then go to the Nile. And the idea came from, we started working in Ethiopia actually a long time ago, because in the university we have a lot of collaboration with the African scientists and with the Addis Ababa University. And the Ethiopia is a spectacular land. It's broken by a rift zone that going down to afar when we have looking at the new ocean and placing basically. But then you have the highland, and the highland is constituted composed by a million kilometer cube of lava and place in a couple of million years ago, around 30 million years ago in the Oligocene. So it was an enormous amount of lava that flowed all the area and was very low viscosity lava, so was able to flow not like water, but almost. So arriving to Somalia and Yemen. So you have to imagine that Arabia was the Red Sea and the Gulf of Aden was not open yet. So you have to close Arabia and join to Ethiopia and Somalia, to the Horn of Africa. And then all those land was created 30 million years ago, an enormous fracture zone open with enormous volcanoes, probably having a big impact in terms of CO2 and placement also in the atmosphere at the time for the enormous amount of that. So we were still working on that. Now, if you fly to Addis Ababa, you're descending down to Addis Ababa, it's 2,000 and something meters high. So we were still questioning why it's so high here, and what is related to some deep mantle structure that is uprising that, creating this lava, and then is still producing this high elevated mountain or plateau more than mountain. And so the question was basically this one, and we started working on that, and we realized that the uplift of this area was occurring at the time we had the eruption, the first eruption, 30 million. We already have some mountain standing at an elevation of almost 1,000 meters. So the uplift occurred just before the emplacement, and then you have the big eruption. But then you have another phase of uplift, and still now no one knows if it's uplifting or not now. But so you reach this elevation. So the story appeared to be much older of the uplift than previously thought. Previously, people were thinking that the uplift was a recent story, and we thought that this started at least 30 million years ago. So now the question is, what is the age of the Nile? And so there's a big discussion on that, because the Nile we see today probably was not, of course, the Nile we were seeing before. But we even don't know if the Nile is a recent history, just occurring in the last 2 or 3 million years, as many people think, or if it's an older history, starting previously. Maybe at the time we have the uplift in Ethiopia, and if there was a connection between that plate, Ethiopia, and the Mediterranean. So our work was a collaborative team with plenty of persons working in different places, University of Milano, for example, Florida University, Austin University, but also the National Geological Survey of Israel. So it was a pool of scientists working on the problem, and Roma TRE University, my university, my own university. And so we start asking ourselves, why you have this very long river going down to crossing the most arid desert in the world and going down in that direction for 6,000 kilometers, the longest river on Earth, crossing the driest and arid region of the Earth, and why is going this direction, and why is goes so for such a long time? So maybe a river is at the moment we equilibrate, and if you don't have of course the water go from up to down, and if you don't create a different elevation, the gradient will stop, and so the river will stop flowing. And so you need a mechanism to have a gradient of topography that is keep the gradient constant. So the river eroding, trying to equilibrate that because it's depositing here, it's eroding in the high area. And so it's counteracting. But if you're keeping the gradient, taking this gradient or maintaining, supporting this gradient for a long time, then the river may go in the same direction for a long time. At the same time, we were thinking to that, one of our colleagues in the University of Milan was finding the smoking gun at the beginning of the delta of the Nile, which is an enormous delta in the Mediterranean, that was started depositing exactly 30 million, more or less 30 million years ago. It found crystals that actually derive from Ethiopia, so in a boreal. So the connection was done. And so we start thinking what could be the mechanism to keep, so probably the connection was already there and probably was lasting for 30 million years, bringing Ethiopian material into the Mediterranean. What is the support of that? The mantle may do that. So the upwelling that create all this volcanism is still creating uplift. So keep the high elevated region of the plateau of Ethiopia for 30 million years ago, or 30 million years. And on the same way, we realize that the Mediterranean, because there are subductions, so the mantle, the Ionian Sea is going down into the mantle, is pulling down all the area of the delta. So you are creating a gradient for 30 million years that is necessary to sustain the flow of the river, force the Nile River to go in that direction. Of course, it was not the same you observe now, but probably the same direction, something similar. And this was very fascinating. So we do also some modeling, and we call that dynamic topography. It's different from what is isostatic topography, the static topography, which is related to the Archimedes law, so the floating of a body on the water. So the thicker the lighter the body, the higher the elevation, like an iceberg. This is different. The dynamic topography is created by the mantle. And conversely to the static one, it's not a permanent feature, but it changes in time. So during the mantle upwelling, you expect to have elevation, but then you can have downwelling on the other side and you have subsidence, and you create a circuit, a convection cell. The convection cell, like the one you can have for all convection process, it created a different in elevation. So what we done is reconstructed a convection cell in the computer using the seismic imaging that we have in North Africa. So when we put the data in, the convection cell just rise up, and we can predict the amount of uplift that you observe with this due to this process and subsidence on the other side. And we compare that with what we observe
So that means that the uplift is still going on in present day and still in somewhat counter leveling the leveling of that the river wants to do.
So we don't know that actually, see if this really keeps going, but for sure, what we suppose is that
scientifically, yeah.
Not sure in this kind of business, unfortunately. But our calculation tell us that at least 600 to 700 meters of the topography of Ethiopia is supported presently by the mantle. Let's say that if you stop that, you should expect to have some subsidence, okay? For 600, 700 meters, it should go down. It's just supported like you blowing the hair and then you, like a balloon and keep going up. And if you stop that, then it will it should go down. That's what we predict. Now, we don't really know if it's still active, uplifting or not, and at what stage we are. The only way would be to have, for example, leveling different years to do a leveling network and then to explore that, or GPS, even install station and observing that for a long time enough to overcome the error on the vertical. That's provide us maybe a result on the actual situation of what is doing Ethiopia. But no, we don't know exactly what he's doing. We can predict how much is the excess topography due to the mantle now.
Now, we're still talking about at least 2 million years for the last big changes to 30 million years in where this process has started. Is there a possibility to, from a geological perspective, evaluate how the river has looked, let's say, in the last 50,000 years only? Or is the resolution of geology too big to say we know exactly how the river was running in the last 50,000 years?
Our dating methods, it's providing us constraint on the resolution of the time scale we can observe. So we do have a pretty good time record when you observe the dating method, for example, using cosmogenic, provide us a good idea of what happened, as you say, in the last, for example, 1,000 years or 2,000 years or some 1,000 years, okay? But then we have a gap on dating method. So then it's going to be a little bit more difficult to explore what is the intermediate time scale, like a 50 to 100. So for the resolution of the river network at very, like in 1,000 years and things, there's plenty of study done and it's perfectly done. So very high accuracy. What we don't know is basically if you ask, and then we also know the Nile have done fantastic things. I mean, you probably have heard that, or you may not, that for during the Messinian, 5.8 million years ago, the Mediterranean was completely dry, almost completely dry. So as for some reason, probably due to the closure of the Gibraltar Strait, for tectonic reason again, because there was a collision from Iberia to North Africa, the Gibraltar Strait rise up and close the gate. And so there was no more possibility to refill the Mediterranean with fresh water from the Atlantic. And then you have a very sharp drop down of the water sea level, almost a couple of kilometers. In this moment, we start depositing a lot, big, thick, very thick salt layer. That was deposited exactly that time. Part of that, we use it for like a salt in our dinner or on our table. It's a pure salt, fantastic. And it's Messinian in age. And at that time, many of the river produced a big incision. So the Nile at the time was inciding so much that it's probably, if you go to Cairo, some tests observe that you have an incision of more than hundreds of meters, even there, you know. So you have that the entire northern Egypt was a big canyon while this Nile was going down, but also the Rhone River and many of the rivers. There was a complete reorganization of the system. It lasts for 200,000 years, and then you have the refill of the water afterwards. It's an incredible, dramatic change in the water condition of all the river was inciting so much. So can you imagine if you increase of 1,000 meters the elevation of the Alps in a moment, like instantaneously? Can you imagine the impact that can have also on the massive destruction of the mountain, erosion, incision of the river, earth shape, everything. So that kind of we know quite well this moment. We are able to reconstruct quite precisely, and also we know very well also the delta. So at this time scale, it's probably well known. Then we have gaps of known unknown, and this is due to the dating methods. So we have radiometric dating. We use isotope to date rocks, and also other like cosmogenics, the exposure to cosmogenic light of crystals. So we have plenty of different methods, but sometimes we have gaps, and so we don't have the full story.
Of course.
Yeah.
So that means that because the sea level was getting lower, and you had this salt layer basically, or this mixed salt layer, then the river was cutting deeper than it would have if there was no if the sea level was still higher, and it
Yeah.
was the damping mechanism of
Yes,
of, of
something like that. I mean, of course, I mean, when the water sea level of the Mediterranean go down, first you have the position of gypsum. Gypsum because of course, because of evaporation, just because of,
Mhm.
so thick layer of gypsum everywhere. We have that in Italy, and we have in Greece, we have that in Spain, everywhere in the Mediterranean you can find that. It's very nice. So it's a reference level. And this was probably occurring also if the water was still there, but not that much. So you're accumulating the deep in the Ionian Sea, 4,000 meters, we have evidence of gypsum at 4,000 meters now depth in the Ionian Sea. So at the time, of course, if the drawdown of the sea level, all the river was inciting so much, creating narrow gorges like the Grand Canyon, of course. So the northern, you may imagine that the northern Egypt was a Grand Canyon, like a structure with the Nile going down so deeply. And then you have a big flooding arriving after in the Zanclean, just few thousand years after, flooding everything and filling everything. All the canyon was filled by the sediment everywhere, the Pleistocene sediment arriving, the new sea fresh water, and this created, of course, it's amazing, an amazing impact on the shape of the landscape shape, of course. So the Nile was eroding a lot at the time, of course, and producing a lot of erosion and incision in northern Asia.
Sorry, I didn't catch that correctly. What was the event of the flooding? What was the...
Pliocene, Pliocene, in the Pliocene, the lower Pliocene, Zanclean, the Zanclean, but in the lower Pliocene.
Mhm.
So after just after the Messinian, 5.8 at a few 100,000 years after, you have a big flooding event. So the water sea level rise again, and so overcoming the dam on the Gibraltar Strait. So the imagination, we think about a big waterfall of water arriving. In fact, it was more complicated. It was seaways going also around.
Yeah.
So it was not only the Gibraltar Strait, also in the Messinian, it was seaways. So it's more complicated than that. But in the imagination of the first scientists that discovered that big impact was a flooding event. It was a big discovery.
If we have this massive like cataclysmic events that shaped Earth in relatively short periods of time, if you think about like old stories, like for example biblical stories, when they tell about flooding or they tell about primordial waters and they tell about these huge events, or that fire was raining from the heavens, or so do you think that they could have been inspired by those events and then condensed into those narrations?
They suggested that some of them may be observed. Actually, some of the story may be observed, like the, the crossing the Red Sea, for example, or cataracts form, for example, when the Black Sea entered in the Mediterranean. There was a different elevation, so it has been reconstructed. That there was very recent episode of flooding from the Black Sea to the Mediterranean. There was a different. So there's been some event that maybe happened recently, and maybe inspired the imagination also of this all this biblical. Of course, in the Bible there are things like I don't know. Drawing episode. I mean, this is climate impact, and things like that that are clearly something that we observe in historical time, plenty of times. So this is possible. Also, we may think about earthquake, big cataclysmic earthquake that create, for example, it is well known that in 385 before Christ, there was a big earthquake in Crete. These you can, if you go in Crete, you can find the Roman old harbor Roman that is standing at 8 meters of elevation above sea level. So this create a big uplift on one side of the island, but also it created an enormous tsunami that has been registered everywhere in the Mediterranean and has been well documented. And this is a kind of cataclysm that you're expecting. The tsunami has a very large impact at the scale of the Mediterranean, where the civilization was actually. So you can feel it from one side to the other of the Mediterranean, and the people that was living in the coast may be actually affected as the one that hit our coast more recently, for example, in Sumatra, and after the Sumatra earthquake. So tsunami is really something that may have also a big impact on the imagination, and maybe have been, I don't know, somehow, if observed, or big eruption, of course, like Pompeii, for example, something like that.
Yeah, like this historical event.
So can be, and we had before that Santorini eruption for sure. Produce an enormous caldera in Santorini. It's well known, and this may be also, somehow is known. So also big tsunami, big eruption. Maybe yes.
Now I have to test your scientific how do you say, resilience one more time, because I want to ask you if a storytelling device. How would you react as a geologist if you would read it in a book? Would you say, "Oh God, that is so stupid," or would you say, could be, because sometimes you read in the newspaper that someone was building a new home, a new house, and they had this thermal heating drilling, and then they hit a gypsum layer, and then the whole village was like slightly rising a little bit because there was water going into this layer and creating a huge damage. So my idea was, could it be possible for a bad guy to somehow like blow up a dam or have massive amounts of water running into a mine where there is somehow a gypsum layer in the earth, and then making a plateau rise, and that causing a whole river to take a different direction. What is that? Is that even possible, or is that just complete nonsense from a scientific perspective?
I don't know. Salt is it's a really peculiar material rocks. It's a really peculiar rock. So salt, it's behave really incredibly. First of all, from a rheological point of view, it behaves like a ductile way. If you have the possibility to go or to look at picture of the Messinian salt mines in Sicily, for example, you will see the splendid and fantastic fold that this salt is doing. So to carve the salt, they open a road into the mine on the earth, of course, and the road is closing every year. So they have to cut because the salt is really flowing. So it's time to close the void, of course. So it has a very particular beauty, and also as being a very low density material, it also has the tendency to rise at the time scale, not quickly enough, but you can find we call it salt domes, so rising, popping up from the clay. If you go in southern Italy, for example, in plenty of places, you have this Messinian salt popping up. So it creates a little diapir that is going up. But the water destroys the salt, dissolve that. So you pump water into soil, into salt, then you have dissolution of salt. And so you don't create a plateau, but you create subsidence. And this may have
So it's sinking in, basically, because it dissolves.
You can create sinkhole, for example, big sinkhole. So you create a large depression that may crack down also instantaneously, creating big damage. So we have plenty of area where building on top of a salt layer, and if for some reason some water arrived there, then you can create a big crack and then collapse on the surface, and you can have a sinkhole. So the building may affect, and there's also a big risk for human, and it's a big source of risk. So we need to know where is the salt, and if the water going to the salt, then you expect to have dissolution, and then if you have dissolution, of course you create the void, and then you have collapse. That's that's the typical feature that we observe several times on the Earth's surface related to that. The salt may also uprise, but the time scale to do that is very long. So thousands of years or millions of years. So you can have diapir, but this is a different story. But with the water, you have collapse. So
if you build the mechanism, you don't go for rising because it takes very long. You go for the collapse. Would you find in sub-Saharan Africa salt, or is salt only found near the oceans, or
no, salt, several places in the salt is everywhere. For example, salt deposited exactly when you first create a basin. So if you go in Afar, for example, you have active salt depositing, like in the Dead Sea. No, you go in the Dead Sea, you are beautiful, no, salt depositing now. So this is the environment where you have that. So you create a basin, and so this basin is going down, and then you have some water arriving, like in the case of the Dead Sea, the Jordan River, bringing water, and then evaporate and leave the salt there. Okay. So every rift zone, when the one plate drifts apart from the other, at the beginning have salt. So we have salt everywhere. In the Triassic, below many of the Mediterranean mountain, Tethyan mountain belt, because there was creating this oceanic basin in the Triassic and Jurassic. So you have salt everywhere, from Gibraltar to Asia. And for example, all the sequence have this salt layer at the base. And this salt layer is creating also a geological difference. So with the mountain, when you create a pile, when you pile up one slice of a mountain on top of the other, the décollement run into the salt, which is the weaker part. So, so you have plenty of salt everywhere, not only near the ocean, but also below the mountain. And this is creating also some landslides, big landslides that can also accommodate along the salt, but also the big fault, as I said, can create that. So we have salt everywhere. And then we have more recent salt or very old one, like the Triassic one. And it's pretty well known, the salt, and also it's dynamic because it's create traps for hydrocarbons. So all the hydrocarbon geologists know very well how to treat and to look for salt in deep interior of the earth.
Now, for a last question to wrap this one up, I wanted to ask you if you had a wish and you could answer one question in the geological sciences, something that you really wanted to know, but so far there is no chance to get evidence or to find the right thing. Would there bring a topic to mind where if you had a genie, I would want that answer. If I just had an idea how that worked, or is there a big blind spot in geology where it is really difficult to get any idea what happened there, or is there?
Oh, that's a very nice question, and I have several of them. I have several spots that pop up in my mind um, uh, I don't think we have a clear idea of how to create big mountains. So, what are the forces at work and what are the mechanisms to create the Himalayan Tibetan plateau, for example? So, this enormous mountain. So, that kind of question are deeply in my mind. About that, and I think that it wouldn't be fantastic to have the possibility to really understand the mechanism that is producing that and the way it's doing. I mean, how a big plateau like the Tibetan one is creating and is uplifting and understanding. That would be for me already a big step. There are plenty of people working on that. There's plenty of ideas running around on the formation of the plateau, like the one, the Andes, for example, or the one on the Tibet, on the Iran, something like that. This is a very interesting. This for me, mountain, region of orogenic belt and the mountain are something that I think we still miss fundamental ingredient. So we have a lot of work to do on that.
Well, Professor Faccenna, I thank you very, very much for doing this. I think we've reached the end of a long conversation now with a lot of topics. Thank you so very much for taking your time and for doing this. And yes, I hope maybe we can do this another time. I think there's still plenty of topic on geology that needs to be addressed.
It will be my pleasure. Thank you, Matthias. Very nice, interesting conversation.
Thank you.